In this video, we're going to introduce the concept of sets, which is basically a well-defined unordered collection of distinct elements. So basically we have its limitation or scope represented by curly brackets, and you will put elements here, say shapes or any elements. So for this particular set, we could have a name, for example, and we can say that shape triangle, for example, is an element of set A. You can also say like the circle is not an element of set A. So the concept of sets doesn't involve order. So for example, in the previous set, say set A, we can say that this is just equivalent to, or this is just equal to, in this case, so this set is equal to another set but with a different order. So you have shapes, same shapes. So they're just equivalent. Even if we are going to have a set that has repeated elements, say in this case, this is still equivalent to the original set A. What if the set doesn't have any elements? Say, what if I have a set B with no elements at all? So we call this an empty set or a null set. So we could also symbolize B as a null set symbol. How about, is this equivalent to, say, set C with this symbolism? And basically this is not equal to set B. The reason is, for example, the cardinality of set B is a null set, so the cardinality is 0. For set C, however, the cardinality of set C, or the number of distinct elements, will be 1, because it contains one element, which is in this case an empty set. So with that basic ideas, we could also have a case in programming, like integer, for example. The integer data type is also a set. So when it's 2 bytes, for old computers and microcontrollers, you have a set of integers from negative 32,000 to positive 32,000. So when it is 4 bytes in modern computers, you have this 2.147 billion positive to negative to positive values. And we could say that the integer data type is a subset. So this is a subset to our mathematical integer set Z. So we can say a subset if it has less than elements or equal to the actual set, that is given that the elements are common. So we could also have a proper subset. Say, let's come up with a set 1, 2, 3. So if I have a set A that is 1, 2, 3, 4, then I could have a subset B which contains elements, say 1, 2, and 3. So we could say B is a subset to A. However, the question arises, can B be equal to A? Say, can this B be 4, and can I still consider it a subset? And the answer is yes. So B is still a subset to A. However, we can no longer say that B is a proper subset to A, because for a set to be proper subset, it should have less than elements than the original set. So this is the symbolism for that. This is a proper subset. So finally, we have the notion of power set. So for example, you have a power set. Which is basically the set containing all of the subsets of a particular set. So for example, if you have a P of, say, B, so let's come up with set B with 2 elements, say A, or just use numbers, so say 1 and 2. Then the power set of B will contain, it could contain set containing A, or 1, containing 2, containing 1 and 2, and finally the set containing no elements, or the null set. So when we formalize this, this is basically, or this can be expressed by twice raised to the power of the cardinality of the set. Say cardinality of set B is 2, so this will be 2 squared, so you have 4, and that is basically the cardinality of the power set. So again, this is just a very rough introduction. We could also introduce the notion of set builder notation. So you could define an int, for example, data type, as a set, say x such that x is an integer and that integer is between these numbers, for example, for 2 bytes. So that means I could define it as negative 32,000 and then positive 32,000. So set builder notation, still the curly brace, and it's well defined property. So pretty much that's the basic.